All right, hello and welcome back. So we were talking about inheritance, which is a very fun thing. It's just made needlessly complicated by C++ for no good reason. But hopefully you get the gist of it, and that is essentially all that needs to be said for this class. It will help you quite a bit as you continue your computer science career, though. So we were talking about virtual methods because sometimes, like if we use a cat like an animal, like the type of it is actually animal, we would like it to do the cat things if we overrode them, okay? Not the original animal, like animal noise thing. We'd like it to do the cat thing because we spent so much time overriding that same method, okay? And we use the virtual keyword for that, and also the override keyword. And that brings us to virtual methods. So we were talking about what happens, and let me give you some more examples now. So I've written a little bit more here. So I've copied in everything that we did last time: animal class, dog class, cat class. They all, cat and dog, derive from animal. And then down here, I'm showing you that, well, just to remember from last time, we noticed that we need to make a vector of animal pointers. Technically pointers or references would work here. And then finally it's going to use the vtable, or this virtual method is going to be called properly. It's going to use something called the vtable, which I'm going to talk about in just a second. So depending on the original class. Which is all well and good. And so we'll finally see Go Dogs Go and Meow for that. Oh no. There we go. And so now I have added a few more things. Here we go. Just to highlight the problem. So here's where we were before. We got our Go Dogs Go and Meow, which is exactly what we wanted. So here's the idea. We are forced, if we want to use virtual methods, to go through a pointer or a references. Okay, they won't work correctly otherwise. So I can make an animal called cat1 and set it equal to something that is a cat. Use the cat's constructor. But when I use this talk method, sadly, I'm going to get animal noise back. So this is the same problem as the original one. So this doesn't actually do what we wanted. Overridden cat method. Okay, so that's no fun. And so you are required to use either pointers or references, and that will fix this problem. Okay, so if we use pointers instead, animal cat2, make it on the heap, have it talk, suddenly, we're getting a meow out of this. It's going to actually call the proper method. That's beautiful. And also, if you were to use references, that would also work. Make a reference to an animal that is itself a cat, okay? And tell it to talk. Oops. Again, we get meow, which is exactly what we wanted here. So you have to use either pointers or references if you mismatch the types, okay? That is required. So, okay. I think I should probably have put these in the opposite order, so let's do that now. A virtual method is for what's known as dynamic dispatch. On the fly, as the program is running, C++ figures out, oh yes, I need to call the cat method. I need to call the dogs method, not the animal's original method, even though the type of this variable is an animal, okay? So regardless of the type again. That's how that works. And the opposite, the thing that went wrong, is potentially a feature in C++'s mind. That's called static dispatch. I can't talk tonight. So that is what's going on here. So we don't like static dispatch. We want it to usually always have dynamic dispatch, so we're going to use virtual all the time. And the second you start overriding those important big three things within base classes and subclasses, oh man, do we run into issues. So you should always remember to use a virtual destructor if you ever override a destructor somewhere, because otherwise it'll run the wrong one and it won't clear all the memory, okay? We don't want that. So that is virtual methods in a nutshell. I'm going to give you some more examples, but let's talk about how it actually works under the hood. So it's slightly complicated. You don't have to pay attention to this if you don't want to. You can skip ahead. But this is exactly what C++ is doing under the hood to allow these methods to get called in the right way. Okay, so when you use a pointer or a reference, it looks up which function to call inside of this thing called a virtual table or a vtable. Okay, so each class, it gets its own little vtable that maps method names to implementations. So we have the cat vtable, we have the dog vtable, and we have the animal vtable, because you can make animals just by themselves. And among other things, well, I guess this time there's only one virtual method, so there is a talk method defined in all of these. Okay, there's a different one because they do different things in each class, remember. Okay, and so the idea is anytime you use references or pointers to call a method that is overridden, that is virtual, what happens is it's looking up in the vtable what's going on here. Okay, so every time you make an object, you say like cat C, really, under the hood, it knows that C is made up of a cat. Like it stores that information. It stores that information about the implementation of the cat class, and that links to the vtable. So it's got a vtable pointer. Just like this, that's pointing to, the cat has other fields of course, but one of them is secret. It's called this vtable pointer, and it's pointing to cat's vtable. Okay? And if you make a dog D, it'll do the same thing. It'll have this secret, among other fields, a vtable pointer to dog's virtual table. So it knows then, if you ever use a method call via references or pointers, it knows to consult the vtable to figure out which method to run. Okay, that's all. It's a fancy implementation of a simple idea. Okay, that's how it works. It just goes and looks up in the table, hey, which function do I need to call? Which method? All right, so let me now give you one last piece of information, and then you know pretty much all of object-oriented programming. So I hinted this word called protected. It's a keyword. It is the third and final thing along with public and private. Okay, so let's pretend it's Victory's birthday. So let's change his age without the setter. Okay, we want to say age plus plus. Gotcha? So obviously, we can't do that in main. We could try to give him a birthday in his own little class. So we can say void birthday, and that can do age plus plus because it does have an age member variable. We inherit that from animal. But you can see it's underlining it. There's a bit of a problem. So Victor E dot birthday. Please have a birthday, Victor E. And you can see out his get age after that. Sadly, this will not work. Oh no. Okay. And the reason is because its age, inside of the dog class, the age is private. It's private to animal. Ooh, but it's a subclass. Shouldn't it have access? And the answer is no. It doesn't automatically get access to a private thing. Anything declared private belongs to the class and the class only. So if we use private, everything below only belongs to the animal class. And you would be forced to use getters and setters. Even though that means that you don't get access to these things even in derived classes. That's the meaning of private. It's local to the class only. Okay, so you can make animals, and you can make methods up here that work with the private member variables, but you cannot touch these private member variables in any class that inherits from animal, even though they do have them. Okay, like every dog, every Victor E really does have that variable. So he's got name and age and school or college. Okay, these all exist, but we can't access this unless it is what's known as protected. Okay, so taken from animal, we can't access them directly without using protected. Without making them protected, let's say. Okay, that is the idea. Oops, I should close this. And that's the key. So private is visible inside the class only, and not even to subclasses. But protected and a subclass is just the same as a derived class, remember? But protected means that this thing that you're working on, it's actually going to be visible inside a class and all its subclasses. So it's like in between public and private. So it's not visible to outside, but it's visible to yourself and any of your subclasses. So we would, instead of using private here, we should use protected. Now, all these things are shared with, that is, they're directly accessible in any derived class. Okay, so now suddenly, because we say protected, we can get access to this age. Okay? Okay, so now age++ works. This will actually compile because there's no access specifier problems. And Victory started with age 3 is now age 4. Happy birthday, Victor. Okay, so that's protected, and now you are experts in object-oriented programming. So you now know about the 3 pillars of OOP, if you have ever heard of these before: encapsulation, polymorphism, and inheritance. That was the final piece. Okay, so just to spell them all out, you might hear about these in an interview question one day. Encapsulation, it's when you hide implementation details, so you know about that. That's your public/private/protected. That's using classes to hide information from the user. Information hiding is another name for it. And also, data and code are packaged together. So like in a class, it has methods and fields. Okay, so that's another way to think about encapsulation. Polymorphism is a very fancy word. It just means many forms, polymorphism. So many forms in Greek. It just means that you're using the same function or method in a different way under different contexts. There are 3 different types of polymorphism that are common, and you secretly know about all of them now. You just haven't heard them called by their name. Okay, so I'm not going to test you on any of these things. It's just for your knowledge. All of these 3 things are considered polymorphism. Okay, ad hoc polymorphism is when you use the same function or method, and it works differently given different types. So like if you add 2 ints using the plus operator, it will numerically add them, whereas if you use plus on strings, it will concatenate them together, which is a different operation. So plus is overloaded. It's polymorphic. It knows if you give it 2 strings to do one thing, or if you give it ints to do another thing. So many forms. So it's actually the same symbol, but it has many implementations. Okay, many forms in that sense. Parametric polymorphism is something you learned in this class. It's when you use templates. It's when you write something generically, like the types don't even matter, and it works the same regardless of those types. So you're always going to use a template for a parametrically polymorphic function or method or class. So, for example, getting the length of a list, given a pointer to its head, does not require you to know anything about what's stored in the list, what the values are. You never need to look at the values of the list to figure out how long it is. You just need to follow next pointers, right? And so if you had a templated node struct, then you could work for lists of ints, lists of doubles, lists of strings. It doesn't matter. So that's parametric polymorphism. And then subtyping is when you use inheritance. So it's when you use inherited methods to perform different tasks. So that is exactly what we just did with these virtual methods. Okay, so we made the same method with the same name and the same symbols, like void, returns nothing, takes nothing. We've implemented those in 3 different places, and the compiler or the runtime system is going to pick the right one in each case. So, for example, you can make a speak method that takes by reference an animal, and so when you call a.talk, it will, inside of this method, it will call the correct one depending on whether it was an animal or a cat or a dog, things like that. Okay, so that's subtyping polymorphism. And the last pillar is inheritance, which you're now experts in. It's when you share functionality, okay, between some kind of parent and a child class. Okay, so you don't have to reinvent the wheel. You don't have to make a million getters and setters because they're all implemented in one place up top. Okay, and you can have default implementations of things so that you don't have to always override them. Sometimes the default implementation is the correct one. Okay, so before I get to these next things, let me just show you the quintessential example of inheritance. So, I'm sorry to do this to you, it's just everybody uses this example. So the example is kind of boring, sorry, but it has to do with people, like a person, and then every employee of a certain company is certainly a human, usually. So let's just assume that. And then you can have employees, special kinds of employees, like supervisors. We'll make a supervisor class. And so persons have names and ages, social security numbers if they live in the US. Employees have, I don't know, salaries, and maybe employee IDs. And supervisors have employees that they're supervising. So maybe they have a vector, maybe, of employees that they're supervising. Okay, so this is our hierarchy, and maybe there's one method associated with all of these, like, I'll make it in green. That's like, we can just make like a print method or something. or actually toString. Let's do toString for a reason. So you can say toString. Don't know why I'm using underscores, but I am. Okay, so those are the methods associated with all of these, and we know from experience that we should probably make toString virtual with just to watch our backs later. So supervisor inherits from employee, who inherits from person. Okay, so let's do this. And they all have that one method. Let's do, I don't know, employee.cpp. That's like the hierarchy, or person, employee, supervisor. Let's not leave anybody out. So, first class, person. Oop. I'm going to make this a bit faster now. So, public, every person needs, and I'm going to do this in, I'm going to be lazy like I was before. We should probably implement these things outside classes, and you can do that normally. But I'm just going to be lazy and do it here. So, we're going to have protected member variables. String maybe name, int age, dun, and then we'll do need strings, definitely. I'm eventually probably going to use vectors. So we got all that going on, and then also we have a virtual string toString method. Okay, it's going to be const as well. So this is what that's going to look like. So that's person. And let's now do employee. So we've got, they probably also have a company that they work for, but we're just going to give them salary and employee ID. In theory, you're using this class for your own employees, maybe, so you know where they work. Maybe it's a double. Salary and int employee ID. And it's going to be employee. And this is going to be an overridden toString. It's going to be const override. Okay. And then finally, we can have supervisors. Who maybe take a vector of employees, because maybe the employees are themselves supervisors, who knows, and this is supervisor. Vector of employee stars, and what do we call this? Employees that this supervisor is supervising. Maybe we can just call this supervising. Okay, so let's implement these things. So every person has a name and an age, so you're going to always have string name int age. In fact, we're going to have this for everybody because they're all inherited, and we need to call those constructors. Boop. And then we'll say boop. And that works there. Then employees also have salaries and employee IDs. And, well, so do supervisors, because they are employees. Okay, we'll set up the inheritance relationship in just a second. And then finally, every supervisor is also a person and an employee, and it has a vector of people they're supervising. Okay, so we can make this a constant reference. Isn't that fun? All right, so Now let's set up the actual hierarchy. Person's the base class, employee inherits from person, and supervisor inherits from employee. Okie dokie. And now let's implement all the constructors. Oops. Okay, so we'll say, let's just do this in the initializer list. Name, name, age, age. Same for this one. It can be person, name, age, call the constructor, and then salary, salary. Set them to themselves. And employee ID, employee ID. Bracket, bracket. Okay. This is now employee name, age. We're just calling the constructor. Employee ID. No, salary first. Employee ID. And then we have the body that is empty. Okay, so those are the constructors finished. Again, you should probably be implementing these outside. And then we can say toString. So every person, let's make a string that is return. Just going to make an empty string so then I can start adding things. Or actually, name will work. Name plus toString of age with maybe a space in between. Okay, so that's how we translate a person to a string. And then we can go and print that out. And it's my fault for doing this. It thinks I'm calling this function recursively, this method recursively. It's standards toString. And it should be happy now. And, okay. Employees toString is, well, let's return whatever the person's toString is with the salary and employee ID attached to that, okay? Attach salary and employee ID to the person's toString result. So you can't just call toString because it'll call your own toString. How do you call the person's version? How do you call your subclass's version? You do, in fact, say person, : toString. Okay? That's how it works. And then plus space, standard toString of salary, plus space, standard toString of employee ID, and that's it. And then we're going to do the same for supervisor. I guess we're going to have to go through the employees as well. So it'll be like supervising. So string result equals the the employee's version of toString on ourselves. So that's going to work. And then we're eventually going to have to return res. We want to add the employees. The supervisor is supervising. And this is going to get weird if one of those employees was a supervisor themselves, but who cares? We're going to tab over, I guess. So for employee star e in supervising res plus equals a new line plus e toString. Okay, maybe we'll tab over as well. How about that? So that should, in theory, do it. And then we'll return that res that we built up. So I think this is good. Let's try this for a few things. Let's say we've got 2 employees and then a supervisor. So let's do employee Lawton his salary is, I don't know, $3.14, and my employee ID is that, and then my cat is also an employee. He makes the big bucks, and I don't know, he was hired right after me. Then we have the supervisor. The other CSCI professor here, his name is Bill, and he came before me, so let's call him my supervisor. I don't know his age. Maybe he's 1 year older than me, and he makes even bigger bucks because he's the supervisor. And he was hired right before me, maybe, let's say. Oh no. There we go. And we also have to give a vector of who he's supervising. And so he's going to supervise both of us. He's going to supervise me and my cat. And so we'll say supervisor Bill, just like that. Yeah, so that should do it. And we can print out everybody's stuff now. We can say cout, well, what's Lawton's information, toString, new line. And the beauty of all this stuff is we've got protected stuff. We've got a virtual method that we've overridden. It's all beautiful. Hopefully it all makes sense. So that's just an extended example. So it compiles. Beautiful. And it looks like I have a small bug in the toString for employee or supervisors. So I'm going to go and fix that, and I'll tell you what was wrong once I figure it out. It appears that I did not set the supervising vector in the constructor. How dare I? There we go. And so here is all the people that is being supervised. Okay, so that's beautiful. Everything is nice. Yeah, I think I'm happy about that. Not sure what's going on here with the doubles, things like that. It looks like something is going horribly wrong there. So let's maybe figure out what's going on. toString age. Oh, there's no space. I see. That was my fault here in the persons toString. We got to put a space right here. There we go. This all looks right. And so everybody who Bill is supervising is going to be tabbed over. And if this person was themselves a supervisor, then it would look very odd. But luckily that's not the case here. Okay, so hopefully this all makes sense and it's exciting. That is my fancy quintessential example. And now the last few things that I want to talk about are not going to be too long or too bad. So the first thing that I want to talk about is inheritance versus composition. And this is really quick, actually. So inheritance, it's for is-a relationships. Like a cat is an animal, an employee is a person, a Jeep Wrangler is a car. That's when you use inheritance, okay? Composition, it's when you have has-a relationships, okay? So these are just fields in your classes. So an animal isn't a name, but an animal has a name as part of it, okay? So every animal inside of their class, like there is a constructor call with stuff inside, every animal has a name. It's part of an animal. It's a piece. It's just a small piece. Okay? Same with age. So these are all parts. Okay? Parts of objects. That's what composition means. Okay? So an animal has a name, a node has an X pointer, it's part of it, it's inside of it, it doesn't mean it is one. And a bicycle, it like has a rear brake, among other brakes as well. So that's the idea. And both of these terms, they can be a bit confusing. Just remember these examples. They're both about sharing things, but the way that they're sharing things are very different. Okay, so an employee is a person, but a salary is something that an employee has. So an employee has a salary. It's not an employee is a salary. Okay, so we're using composition when we're building up the internal parts of every class and its objects that are made from it. Okay, so the final thing that I want to talk about, and then you're out of here, is what's known as an abstract class. So you can make classes that you can't actually create objects from. Okay, so you can have an abstract class called, like, I don't know, abs, and you cannot make an object called A of that class. You can't do this. You can force C++ to be like, no, this was an abstract class. You can't actually make an object of it. You have to just subclass it, okay? So it's meant to be the superclass for a subclass, and it specifies how it needs to be implemented, okay? So that's what it means. And then a pure virtual function is a virtual function that is not implemented in the base class. So it is declared, though. And that means it's going to force all derived classes to override the function. So anytime you have these are all just long words, I know. I'm going to give you an example in just a second. Any class with one or more pure virtual functions is what's known as abstract. Okay? And so how in the world can you implement something but not get a compiler error for not implementing it? How do you not implement something and then not get a compiler error? And the secret is, this is how. To make a pure virtual function, one that is declared and defined but doesn't exist, in a weird way it's defined. You say, okay, here's my function. Instead of putting a semicolon right here, you put equals 0. Okay? That's the key. If you add this equals 0, it marks the fact that it's a pure virtual function. Okay? And that means the class that contains it is now abstract. Okay? So my best example is contrived. I'm going to have an abstract class. Let's make an abstract class called canPrint. And it's going to have one pure virtual method that's called print. Okay? Which return, I guess it's void. And we're going to say virtual void print equals 0. Okay? That's how we're going to say it. And let me write this a bit cleaner now. Semicolon. And then every class that knows how to print things, like an int printer, will derive from canPrint, and then a string printer will also. You can do this for any type. And so we're going to then override print. So one of the nice things about base classes that are abstract is it forces you, if you have an implementation of that class, you know that you have been forced to implement every virtual function. So everybody who derives from canPrint, we know they have a print function inside of them. We know all derived classes have a print function. We couldn't use them otherwise. Okay, they're forced to. So that's an abstract base class. Let me do this. Abstract.cpp. So we're going to make a canPrint class, and it's going to be an abstract class. So this is a pure virtual function. No, that means this is an abstract class. So for example, I cannot make any objects of type canPrint. It will give me a compiler error. Boop. Ah, it even knows. So you say this. And so in main, can't declare CP to be of abstract type can print. Aha, because the following virtual functions are pure. Oh man, it's as if these words I've been saying, other people use them too. Okay, so they force, anybody who implements can print is forced to implement the print function, the print method in order to use them. So class int printer, perhaps. I'm just going to be very lazy and make an int that it takes public, and then we're going to say void print override and go and implement that. Okay? But we need to also say that this inherits from can print. Okay? That's the idea. And maybe this can see out I with a new line. Okay, that's our can print. Hopefully that makes sense. So we can't make a can print because it's virtual. But we can make an int printer. Maybe we'll call it IP. IP.I is 42, and then we'll say IP.print, and bam, it'll print 42 for us. Beautiful, and we can do the same for string. And so we'll say string printer sp sp.s equals hi mom sp.print. Okay? And so this will print hi mom. So the idea of this base class is anytime we have somebody that inherits from this, we know that they have a print method that they implemented themselves. We have some very strong guarantees about that. So this is like an abstract base class can be used to define what's known as an interface. Like, okay, I know that I have available this print method because I've implemented the can print abstract class / interface. Okay. This might seem stupid because now, like, okay, oh, sorry. This is supposed to be public can print. Public can print. If you don't put anything, it inherits privately, which is no fun, but that's okay. It still works just fine because we're not calling anything from the base class. So, yeah, this might seem stupid to you because now you suddenly can't inherit from anything else, but the last thing is you can actually implement, or you can inherit from multiple classes at once. And that's where I'll leave you. You can have multiple base classes, like, all right, somehow, I don't know, an employee inherits from both, like, human and I'm not sure, like, can print. Okay, that's the idea. You can have multiple base classes if you would like. It's totally possible. You just use commas. This is something I won't teach though. So that is inheritance in a nutshell. We've come very far. You are very advanced now in your knowledge of object-oriented programming. So go forth and change the world. All right, some quick exercises and then you're out of here. It might be a good idea to try making a hierarchy of non-empty binary search tree node types. So for example, tree node can be the base class, the parent class, and then internal node and leaf node can be your two subclasses. So an internal node has left and rights, leaf nodes do not. And then build up a tree using just those. internal nodes. And leaf nodes, tree nodes, you probably want that to be an abstract class. And then find the minimum node using this implementation. Okay? That is a very good exercise, I think. And then the last one is come up with an example where you'd want to do subclass : protected parent, or subclass : private parent, rather than subclass : public parent. When would you want to restrict the public / protected properties of the parent class? When would you want to do that? It's hard to find an example, but I think if you think hard enough, you will come up with one. Okay, so that's all I have for you, and yeah, I will see you later.